Can we reach another star? What do we think? At first, the answer seems obvious. No. The distances are too vast, the journey too long, the speed of light, an unbreakable limit. Everything we know about physics says it's impossible. But then, relativity enters the picture. And suddenly, the answer changes. Because under the right conditions, you can cross the galaxy within a human lifetime. You could leave Earth and reach stars thousands of light years away before you grow old. So, which is it? Impossible or inevitable? Because the truth is, interstellar travel is not forbidden. It's possible, but the price you pay is far greater than the distance. We have always looked at the night sky and wondered, what lies beyond those distant points of light? Are they suns like our own? Do worlds orbit them? Could we ever go there? For centuries, the stars were simply decoration, unreachable, eternal, infinitely distant. Then science changed everything. We discovered that stars are not lights in the sky. They are other suns, entire solar systems scattered across the galaxy. Suddenly, the universe became a map. And once something becomes a map, humans want to explore it. Stories filled our imagination with starships crossing the galaxy, civilizations expanding among the constellations. Movies like Interstellar showed explorers traveling through wormholes. In those futures, the stars feel close, reachable, inevitable. But real physics is not written by screenwriters. And the deeper we study the universe, the stranger the journey becomes. Because interstellar travel is not just difficult, it is governed by rules so extreme that the dream of reaching another star becomes something far more unsettling. Not impossible, but profoundly strange. Let's try to understand the true scale of our universe. The closest star to Earth is Proxima Centauri. Distance, 4.24 light-years. That sounds small, but a light-year is the distance light travels in 1 year. Light moves at nearly 300,000 kilometers per second. In 1 year, that becomes almost 10 trillion kilometers. So Proxima Centauri lies more than 40 trillion kilometers away. To understand that scale, consider the fastest spacecraft humans have ever launched. Voyager 1 travels at about 17 kilometers per second. At that speed, reaching Proxima Centauri would take over 70,000 years. Human civilization itself is barely 10,000 years old. Even if we built a spacecraft 100 times faster than Voyager, the trip would still take centuries, and Proxima Centauri is only the nearest star. The Milky Way galaxy contains roughly 100 billion stars. Its diameter is about 100,000 light-years. If space exploration worked the way science fiction often imagines, a galactic civilization should spread across the Milky Way in a few million years. But our galaxy is billions of years old, and we see no evidence of such civilizations, which raises a haunting possibility. Maybe the stars are simply too far away. But distance alone is not the real obstacle. The real obstacle is acceleration. Our bodies evolved under a very specific condition. Earth's gravity. 1g push much beyond that for long periods, and the body begins to struggle. At 1.5g, people can survive for extended periods. but stress accumulates. At 3 to 4 grams, blood begins to drain from the brain. Vision narrows. Consciousness fades. At around 10 grams, unconsciousness arrives within seconds. Sustain that acceleration long enough, and the result is death. This creates a serious problem for interstellar travel. To go anywhere significant, a spacecraft must accelerate. But the faster you accelerate, the greater the stress on the passengers. So we face a brutal compromise. If acceleration is gentle, around 1 g to 1.5 g, then the spacecraft must accelerate for long periods of time. But that means the journey takes far longer. In classical Newtonian physics, the math is devastating. Even if a spacecraft accelerated continuously at 1.5 g, it would still take decades to reach even a fraction of light speed. Interstellar journeys would stretch across centuries. Passengers would die before reaching their destination, which is why many early ideas for interstellar travel imagined something radical. Generation ships, massive spacecraft carrying entire populations. Families would live and die during the journey. Their descendants would eventually arrive centuries later. But then relativity enters the story, and everything changes. The universe has a speed limit, the speed of light. Nothing with mass can reach or exceed it. But something remarkable happens when you approach that limit. Time itself begins to change. According to relativity, the faster you move, the slower time passes for you. This is called time dilation. At the same time, distances in the direction of travel begin to shrink. This is known as length contraction. From Earth's perspective, a spacecraft traveling near light speed might take decades or centuries to reach another star. But from the perspective of the travelers, time slows. The journey becomes shorter. If a spacecraft accelerates at a constant 1.5 g for half its journey, then flips and decelerates at 1.5 g for the second half, the passengers feel a comfortable gravity similar to Earth. Inside the ship, life proceeds normally, but outside the ship, relativity reshapes the universe. As the spacecraft approaches relativistic speeds, distances begin to contract. Stars appear closer. Travel times shrink. Suddenly, destinations that once seemed impossible begin to fall within reach. Now we encounter the second great barrier: energy. To accelerate something to relativistic speeds requires enormous energy. For example, to reach the velocities needed for a relativistic journey to the Crab Nebula, a spacecraft would require roughly 7 × 10 to the 21st power joules of kinetic energy per kilogram of mass. Per kilogram. For perspective, the total annual energy consumption of human civilization is about 6 × 10 to the 20 joules. So accelerating just 1 kilogram of spacecraft to those speeds could consume the energy used by humanity in an entire year. A realistic spacecraft might weigh thousands of tons. The numbers become staggering. And yet, there is a surprising twist. The Sun itself emits about 3 × 10 to the 26th power watts of power. Which means that, in theory, a few seconds of the Sun's total energy output would be enough to accelerate a large spacecraft to relativistic speeds, if we could capture it. That idea leads to one of the most ambitious concepts in astrophysics: a Dyson sphere. a massive structure surrounding a star, capturing a significant fraction of its energy. Such a civilization could theoretically power relativistic starships. But there's another obstacle waiting: the rocket equation. If your spacecraft carries its own fuel, you must accelerate the fuel along with the spacecraft. But that fuel requires additional fuel to accelerate it, which requires even more fuel. The mass grows exponentially. This is known as the tyranny of the rocket equation. For relativistic interstellar travel, the required fuel mass becomes astronomical. In many scenarios, the fuel would weigh more than entire planets, which means a practical relativistic spacecraft would likely need external energy sources: massive lasers, solar collectors, megastructures around stars. Interstellar travel becomes less like building a ship and more like building an entire civilization's energy infrastructure. At relativistic speeds, space itself becomes hazardous. Interstellar space contains dust grains and stray atoms. At normal speeds, harmless. But at 10% of the speed of light, even a tiny particle strikes with enormous energy. A grain of sand becomes a microscopic bomb. Hydrogen atoms become radiation. Shielding must be immense, and heavier shielding requires more energy, which increases the engineering challenge even further. The faster you travel, the more the universe resists. So is interstellar travel impossible? Not exactly. Physics allows it. Relativity even helps. But the cost is extraordinary. Relativistic travel demands planet-scale energy systems, megastructures around stars, civilizations capable of engineering on astronomical scales, and travelers willing to leave their own time behind. The universe did not forbid the journey. It simply made it difficult enough that only the most advanced civilizations could attempt it. The stars are not unreachable, but reaching them may require something humanity has not yet become: a species powerful enough to bend the energy of a star into the engine of a single voyage, and brave enough to leave its own century behind forever. Interstellar travel doesn't just separate you from distance. It separates you from everything that gives your life meaning, from your history, from your culture, from the world that shaped who you are. Because the moment you leave, you don't just travel through space, you fall out of time. And maybe that's the real reason the universe feels so silent. Not because life is rare, not because civilizations destroy themselves, but because they understand something we're only beginning to realize. Maybe advanced civilizations reach a point where they understand the cost. They realize that spreading across the galaxy doesn't create a unified civilization. It fragments it. Each journey becomes a branch in time, a one-way divergence, a permanent goodbye. So instead of expanding outward, they turn inward. They build deeper worlds at home. They simulate universes. They explore reality not by moving through space, but by understanding it. Because in the end, the universe offers us a choice. We can travel the stars, or we can remain connected to each other. But we may not be able to do both. The stars are not unreachable. They are simply unforgiving. And perhaps the greatest mystery is not how to reach them, but whether we ever should. Because the moment we leave, we are no longer part of the world we came from. Maybe advanced civilizations reach a point where they understand the cost. They realize that spreading across the galaxy doesn't create a unified civilization. It fragments it. Each journey becomes a branch in time, a one-way divergence, a permanent goodbye. So instead of expanding outward, they turn inward. They build deeper worlds at home. They simulate universes. They explore reality not by moving through space, but by understanding it. Because in the end, the universe offers us a choice. We can travel the stars, or we can remain connected to each other. But we may not be able to do both. The stars are not unreachable. They are simply unforgiving. And perhaps the greatest mystery is not how to reach them, but whether we ever should. Because the moment we leave, we are no longer part of the world we came from. But what if there is one last possibility? One loophole the universe hasn't completely closed. A shortcut, not through space, but through space-time itself. A wormhole, a tunnel connecting two distant points in the universe, not by traveling the distance between them, but by folding space, bringing two faraway locations together. Imagine taking a sheet of paper, marking 2 points on opposite ends, and instead of drawing a line between them, you fold the paper and push straight through. What was once billions of light years apart becomes a single step. If wormholes exist, they could connect star systems, galaxies, maybe even entirely different universes. Suddenly, interstellar travel is no longer about speed. It's about access. In Interstellar, humanity didn't reach another galaxy by building faster engines. They found a wormhole, a bridge placed near Saturn, leading to another part of the universe, a doorway through space-time. And here's the unsettling part. Wormholes are not just science fiction. They are real solutions to Einstein's equations. Mathematically possible, but there's a catch. To keep a wormhole open, you would need something we've never seen. Exotic matter, negative energy, a form of physics that may not exist in any usable way. So, once again, the universe gives us a possibility, and then takes it away. Maybe wormholes are real, but too unstable to use. Maybe they exist, but are too rare to find. Or maybe they were never meant for us, because in the end, every path to the stars comes with a cost. Distance, energy, time, or reality itself. And if wormholes are the only way out, then the question is no longer, can we reach the stars? But who or what built the door?